Okay, so in the last part of this chapter, and also it's going to be an introductory section to the next chapter, which is going to be the last chapter about asynchronous sequential design. Now, I want to talk about asynchronous interactions. So, when we consider the combinational logic, which we don't have any clock, and the interactions between these gates, or maybe interaction between a clock circuit and the circuit without a clock, like asynchronous circuits, we might have some hazards. We call them combinational hazards because of the timing, like one of the inputs might arrive earlier than the other one. So asynchronous to synchronous ones, the asynchronous signals might cause a hazard. And if you have two synchronous circuits, the signals in between them can be asynchronous. So again, there will be a problem if they have a different clock, especially with the different phases. This will also cause a problem that they might arrive at different times. So we'll see an example how this hazard can arise from a logic circuitry. Here is the first example. So you can see that by using the K-map, we can observe an expression which is it's y and x2 prime and x1, x2. So this is how we can write that up. And if you want to implement this using NAND gates, this will be the expression for it. So then we implement the circuitry. So up until here, there's no problem. Now, when we think about these, that each of them has one gate delay, okay, and each of them has one gate delay, and we have got a inverter over here that x2 will be inverted and it becomes A, and then A NAND Y will give us output B. So x2 is transitioning from 1 to 0. Now, when we consider this as a timing waveform, now if we look at it, so x2, x1, x2, and y are our inputs. So it starts with 1, 1, 1, and this changes to 1, 0, 0, and then 1, 0, 1, sorry, 1, 0, 1, 1, 0, 1, and 1, 0, 1. This is how it goes over here. And as they have got a one gate delay, now when we do any operation, the output will be reflected one gate delay. So when you have got a x2 and x1 as starting from here, let's say 1, 0, then we are going to observe C, which is going to be 1 over here. Okay, so it will be delayed. So let's see how is that going to be done. And A is just x2's inverted, but again, it's going to be delayed. So 1 is there, 0 is delayed, 1 gate, and then 0, 1, 1, and it goes like that. And B is just A and Y. Now, when we look at it, the C is x1, x2, so it's going to be 1, 1, it's going to be 0. Okay, and 1, 0, it's going to be 1, 1, 0, it's going to be 1, 1, 0, it's going to be 1. So one gate delay, we will have the outputs. Now, when we consider B and C together, now this is going to be a little bit tricky over here because, so that's going to be 1, 0, which is 1, 1, 0, which is 1, then 1, 1 over here, it's going to be 0. This is because of B over here. And that 1, so that will cause the problem because A has got one gate delay. So A and Y are not feeding to this NAND gate at the same time. Okay, so you have got A over here, which is delayed. So then this is going to be like 0 and 1, and that will be reflected over here. It's going to be 1. However, it should be 0, like this one. But because A is delayed and then this one is delayed, then this one will cause a problem to have 0 over there, while we are expecting 0 here. So this is known as static 1 hazard. So what is static 1 hazard? When there are two adjacent ones, when you look at the K-map for F, there are two adjacent ones which is not covered. So what we have seen in chapter 3, we just do the ones that we can, and if there are an extra combination, we don't do the combination of those because that becomes redundant. But actually, those redundant nodes are causing these static 1 hazards. So if you include that redundant expression as well, we won't have any static 1 hazards over here. Okay, now, so properly designed two-level OR AND circuit has no static 1 hazards. Now, you might say, okay, are we not going to think as a more simplified expression, optimized expression by using the K-maps? Why do we need redundance? Redundance will be needed if you don't consider as the most optimized design, but you need to consider most efficient design. So again, there's a trade-off between those. And static 0 hazard so occurs when there are two adjacent ones in K-map of F naught. Okay, so F prime is considered over here for static static 0 hazards, and we have to again combine the redundant nodes as well in order to get rid of it. Okay, so when we look at this design now, as you can see, we got the redundant node as well, so we fixed the hazard. Now we have got three gate levels and the one output over here. We still have the inverted X2, but as X2 is also feeding in over here, and Y is also feeding over here, that will actually get rid of that output difference over there. So there won't be any abnormalities in the output. So things that we need to be careful for design of hazard-free combinational network. When drawing loops on a K-map, ensure each adjacent pair of ones is covered by at least one loop. So if cost is not the highest priority, like we said, we need to optimize the circuitry. Then brute force method of obtaining hazard-free network is to use all of the prime implicants of the logic function. And when manipulating the resulting algebraic expression, for example, multi-level gate networks, do not use the identities like x prime plus x or x prime dot x. So you can use distributive laws, De Morgan's law, but do not use this one because this might cause a hazard. We'll see more details in the hazards and how circuit becomes unstable in the following chapter with asynchronous sequential circuits as well. So another thing in the logic design which we consider is the metastability. So metastability, it's the ability of a digital system to persist for an unbounded time in an unstable equilibrium or metastable state. Now, we have got two stable values in logic 1 and logic 0. And if our circuit is in between that means it's a metastable state, so halfway about the voltage. It's not 0, it's not 1, it's just flipping around somewhere here. Okay, that's actually the metastable state. And in the bistable function. So it can occur when, for example, two asynchronous signals combine in such a way that their resulting output goes to an indeterminate state. It's possible to have that. And we can say that metastability may cause by asynchronous inputs to asynchronous logic gates, asynchronous controls to the FSM, because we don't know exactly what time they will arrive. So while that's the case, the sequential circuit might flip from one state to the other. So they can violate the setup and hold times like we have seen it. They might arrive earlier or late, so this will be a problem with respect to the clock edge. And memory cells, for example, latch flop memory elements can stay in metastable state indefinitely. says they are in equilibrium, and noise event or imbalance between the circuits might flip the result to high to low, low to high, so infinite time. And whenever for example, in sequential circuits may cause long input to output delays, and because whenever the input signal does not meet the setup and hold time of the given flip-flop, for example, metastability might occur. So outputs keep oscillates between 0 and 1. And so in the end, it can appear that a flip-flop switches late or doesn't switch at all. So you get out of it's possible. And in order to get out of a metastable state, we either need to force the flip-flop to a known state, like resetting or setting the flip-flop, or we have to wait long enough. We have to put some kind of delay, and we can use that. Or another alternative is using synchronizer. So we put synchronizer. Again, it's not 100% it's going to remove the metastable states, but if we synchronize it with the number of flip-flops, the asynchronous inputs, and then we feed into the synchronous design, at least we can minimize, because we can synchronize with the clock from one end to the other, and then this will be having no combinational delay. So we make sure that we are synchronized and the input is changing the output based on the clock, not by itself. So, and what we have observed is the probability of metastability at the input of the synchronous circuit reduces with every synchronizer flop added in series. And these are generally effective one is 3 flip-flops in series. And in some designs, you can see a 6 flip-flops are used. So this is also possible. And that's all we need to know about the synchronizers and the metastability. And we'll talk about asynchronous sequential design in the last chapter, which will understand how these asynchronous designs can be done. Okay, so there's one simple example in the end. Again, it's a combinational circuit. We have to design a hazard-free circuit. So in order to design a hazard-free circuit, when we design the K-map, we just need to combine this redundant node as well. So when we add that redundant node as well, we won't have any hazard problems. That's all you need to know about. And that's all about this chapter, which we talked about different properties and metrics in digital design, like fan-in, fan-out designs, integration, propagation delays in combinational circuits, and the sequential circuit setup and hold times, which we need to consider in digital logic design in order to have more accurate designs without any problems when we are using clock or clocking devices. Thank you.